Okie dokie. So if you're joining us from the previous video, then you saw how we graphed this parabola that you see below, or maybe you graphed it on your own, in which case, welcome to this video. So let's describe the heck out of this graph. Here are our graph investigation questions here on the side here. And so let's start off with the shape. What the heck does this thing look like? And so one, we could say it's a parabola because that is the technical math term, but I just also want to practice describing a graph to someone who maybe is not familiar with the term parabola. And so how could I describe it? One way that some people could describe it is shaped like an upside down U. So I'll shape it like upside down U, upside down U. Or you could say it's curved. And it is important to point out that it's nonlinear, although that is kind of implied already by these other curved nonlinear, excuse me. Curves or nonlinear, right? But I think upside down U would be totally fine. Parabola, if you just say parabola, you're gonna have to be a little bit more specific because a parabola could be an upside down U or a vertical or a right side up U. And so if I was gonna say parabola, I would want to be a little bit more specific. Parabola opening, in this case, down like a frown. Some people get confused about the way when I ask like which way does it open, and by convention people describe this as opening downward because it's getting wider as you go lower. Down like a frown, or if it was the other way, I would say up like a cup because rhymes help. Right? So I think that gives a pretty good idea of what the shape was if you were to just describe this to a random stranger. Alrighty, so the next question we want to ask, and symmetry is also in here with the shape. And so is there any symmetry within this graph? And again, symmetry is just, is there anywhere where you see the graph kind of mirroring or reflecting on itself? There are other types of symmetry which are not about folding. There is this thing called rotational symmetry, where if you rotate the graph, then you see it on itself, kind of like a pinwheel. This graph, I don't think there's any rotational symmetry. I don't see it in there, but there is definitely reflective symmetry. And so you can kind of see it. And if you follow my ruler here, or you can pretend that this is on a piece of actual paper, if I fold it, say, down along this line, this green line here, if I fold the graph across there, it's not quite going to line up, right? Like this chunk of the graph, this highlighted portion, this green portion of the graph, if I folded it over, it would end up right there, which is not on top of, not on top of the red one. So that's not where our line of symmetry is. I think where our line of symmetry is you can kind of see right down the middle here. I'm going to draw it a dotted line here. Okay. You can see there that if I fold that over, then this point over here, this negative 2,8 point, when I get folded over, it's going to land right on top of this 0,8. And this negative 3,5 is going to end up on top of that 1,5, and so on and so forth. And so that's where you can kind of see where your line of symmetry is. And so does this thing have symmetry? Absolutely does. There is a line of symmetry. There is a line of symmetry. I'm going to abbreviate it SYMM. It's a vertical line. Vertical line through, and then where is it? So I will say a vertical line through the point -1,9 to tell us where it is. Now there actually absolutely is an equation for that vertical line. In this case, it would just be x equals -1, but we'll talk about that in the future. And so this would, if you tell me where it goes through, then I know what it is, right? A vertical line, where does it go? Oh, it passes through this point, so it must be right here. Alrighty, so that's our line of symmetry. Now, if we go into some special points, and the special points that there, depending on the graph, there could be different kinds of special points. But two types in particular are intercepts and the vertex. And so the intercepts, remember, intercepts are where the graph crosses. There's a couple ways to say this: crosses, or you could say it hits or touches. Even just touching it barely would still count. Or if you want to be really mathy, intersect, C-E-S-E-C-T, the x or y axis, axes is plural. And so this is where some people get confused. Intercept, highlighted here in yellow, that's a noun. It's an object. And then this thing highlighted in light blue here, intersect, that is a verb. Okay, so where does this graph cross our axes? Well, this one's very interesting because the y-intercept, oops, sorry, my graph's getting a little messy here. I'm going to answer this question in red. The y-intercept, we can see, is right here at 0,8. Let me scooch that down so you can see. That's our y-intercept. Y-int is how I abbreviate it. So it has a y-intercept at 0,8. Actually, let's write this in sentences. 0,8 is the y-intercept. And where is our x-intercept? We can see those. Actually, there's actually two of them. One right there, whoopsies, and one right there at -4, 0 and 2, 0. So this graph actually has two x-intercepts. Sometimes you'll see a graph with 1. Sometimes you'll see one with 2. There are graphs that have a lot more than that even. And you can even have a graph that has none. All right, so it's definitely going to depend on the graph or /the equation. And so there are two x-intercepts, which are -4, 0, and 2, 0. Alrighty? And the last one here is the vertex. And this is unique to parabolas, although we could kind of, for our purposes, we could generalize the term vertex as any kind of peak on at the top of the mountain, as it were, or maybe the bottom of a valley. And so some people brought this up in class, actually, in that you could identify the vertex on a parabola as the one point that is not mirrored. And so what we mean by that is, hey, this point right here, -3, 5, when it gets flipped over that line of symmetry or reflected, it's at 1, 5. Hey, -4, 0 goes to 2, 0. -2, 8 goes to 0, 8. But -1, 9, because it's sitting on that line of symmetry, it doesn't go anywhere. It is it is its own reflection. And so that the fact that it is alone, so sad, it's alone, means that's how you can identify the vertex. And so this parabola has a vertex of, or at, -1, 9. So definitely we would want to point that out as well. Alrighty. Next up is there a highest or a lowest point on this graph? And on a parabola, this is the vertex, but sometimes there are graphs that are not parabolas where there is a bottom and there is a top. In this case, we could see, hey, what y values are there? So if we use kind of my ruler again, and I'm kind of tracing this graph, basically you can see where does the graph stop existing or stop drawing. So we can see that here, if you look at the top of my ruler, that I still have y values there. My ruler is still touching my graph. I'm still going and still going until I get to 1, 9. And if I go up any higher, that top part of my ruler is not touching the graph anymore. And so where is the last y value that it touches before it leaves the graph? Is at 1, 9 there. And so the highest point is -1, 9, which again is the vertex, which I'll write that there, the vertex. And here's the thing, is there a lowest point? So the way we've drawn the graph, it looks like there is, because we can't draw forever, but we should know by kind of just with our math intuition that if I kept plugging points into this graph, this would just keep going lower and lower and lower. It's not going to turn back up this way. Like this graph is not going to look something like this. That's just kind of not really going to happen, though, based on what we see. And so, excuse me, this graph is just going to keep going downward. And so that would tell us that there is no lowest point. Because anywhere you think you're at the bottom, if you just keep going, you'll go even lower. There is no lowest point. It just keeps going down forever. All right. We can also talk about increasing or decreasing. And that, then again, this is similar to the shape, but remember that it is implied, excuse me, as we go from left to right. That's how we read this, from left to right, similar to how we read English. And so by is it decreasing, it, I should write this in there, it refers to the y values. So whenever we talk about an increasing, decreasing graph, the question is, what happens to y as x goes left to right? In this case, you want to start off as far to the left as you can. And so let's pretend I'm starting off over here on the green dot. If I start here and then go to the left, what happens as I trace along the graph? Well, you're going up, right? So the graph starts increasing, and it's always increasing until when? Because at this point, it changes. So even right here, we can see that the graph is increasing because it's still going upward. It keeps going upward until it turns around right here at the vertex. And so it starts increasing until it gets to the vertex, which is -1, 9. And what happens? Well, it turns around, so it starts decreasing. Then starts decreasing. You'll notice at this point, this is a very long process of describing the graph. We're almost there. Last part, or second to last part, is the growth constant or does it change? So remember, we could identify the growth on a graph by its slope, or we can see, as some people have noticed, the distance between y values. And so we can actually take a look at our table, and that what is the distance? Remember, this is the vertex, so this is going to help us out. Right here, that's the vertex. So what's the difference between these two y values? That's how we can notice the rate of change. The difference between those two y values is 5. The distance between these two is 3. The difference between these two is 1. So I'm just looking at the change in the y values. This one is also 1. And this is 3. And this, between 0 and 5, is 5 again. So this is the growth, right? These green numbers, these represent the growth. Now look, what happens to the growth? Well, it's clearly different, right? Because it's, as we go from x, we increase the x by 1 every time. +1, +1. And so first off, we want to make sure that we're checking as x goes up by the same amount to give a fair comparison. Because you might have the case where, oh, I went up by 10 this time, but you also went 10 steps in the x direction, so that's not really a fair comparison, right? But we notice here that the growth rate is not the same. If it was the same, it would be 5, 5, 5, 5, 5, or 3, 3, 3, 3, 3. The fact that we can see here that it's different, and here's the question. Where is it different? Notice that it's mirrored on either side, and as it gets closer to the vertex, it's smaller. And as you get further from the vertex, the growth is larger or faster. And so here's what I mean by that. Near the vertex, it's small, right? It's 1. And then as you get farther away, it increases from 1 to 3, and then from 3 to 5. And so what I can say down here is, so first off, no, it's not constant. The growth is slower near the vertex, and faster as you go away from the vertex. And you can see that here, that if you were to graph this by checking the slope, like laying a ruler alongside the graph, hey, look, near the vertex, it's relatively flat. And if you trace it along, but as you leave, it gets steeper and steeper and steeper, which is indicative of a faster rate of change or growth rate. The last part here, the x values and the y values. This one's hard to tell, and we're going to get more practice with this in the future, but I could plug in any x value to this, because even though it would be really hard to see on our graph, I could plug in x equals 100 if I wanted to. The point would be like way, way down here, but I could plug it in, right? So in this case, it would use all real x's, or all real numbers for x. And the y values, well, we saw before how the highest the graph ever goes is up to 9, but it will always go downward forever and ever and ever. And so this graph uses y values of 9 and below, or 9 and less, I could say. Whew. Okay, so this is what a full description of this graph would look like. Obviously, I wrote them all in complete sentences, but you could maybe summarize them. But hopefully, this helped you out. It is quite a task, but now you know how you can completely describe a graph. Thanks for watching, and we'll do another example in a second. All right, see you later.